David Smith here with one more flipped classroom math video lesson. 3 tips before we start. First, remember you can adjust the playback speed to make it faster or slower as you like. Second, you can pause the video at any point to catch up on your notes or jot down some questions. Third, you can turn on the captions so you can read my words on the screen. Today's topic, sets and Venn diagram review. So we're going to go through this last chapter and hit some of the high points. Okay, first up, let's do a little bit about notation. This means the set Q contains these 4 elements, these 4 numbers. We had another little piece of notation that we had to work about. The lowercase n followed by Q is asking how many elements are in Q. So in this case, that's 4. Pretty straightforward. Now we had this interval notation, and we also graphed them on number lines. So this means P is the set of all x such that x is less than or equal to 5. I'm sorry, greater than or equal to 5. My brain switched that one. So this is the set of all x, any number that's 5 or bigger. So I've graphed that for you on the number line here. We put a solid dot above the 5 because it does include 5. And then the arrow goes in the bigger direction. So this shows this set in notation. The set now is shown on the number line. Okay, let's do one more. Here's the set of R, which is the set of all x such that -1 is less than x, which itself is less than or equal to 9. Okay, so this x is between -1 and 9. See if you can pause the video and put that on the number line. Okay, so this one's a little bit more tricky because this one is just a less than, and this one is less than or equal to. Okay, so watch this. What we do is here's my -1. I do an open circle there because that tells us that we're not quite including -1. It's getting really close, but it doesn't include it. Now the 9, I put a solid circle above the 9, and then I can connect them. So that's the interval shown on the number line for this particular set. Okay, in this chapter there are 4 already described sets that get referred to quite a bit in mathematics. So we talked about those sets and then they get used over the course of this chapter. So let's review them real quick. We have natural numbers, integers, rational numbers, and real numbers. So you're going to need to know what's inside each of these sets. Now I'm going to go from the most specific to the most general. And something to remember is that as you get more general, each of these new sets includes all the numbers from the past set. So in a way, we'll talk about subsets in a minute, natural numbers is a subset of integers, which is a subset of rational numbers, which itself is a subset of the real numbers. Okay? So pause the video, see if you can figure out what each of these sets are, see if you remember. So natural numbers are like so. So we don't include 0. It's sort of like counting numbers. In fact, there used to be a set that was called the counting numbers, and I think that's what the natural numbers became. But we start off with 1, 2, 3. The dots indicate that this just goes on forever. So these are the natural numbers. Now, integers is just like natural numbers, but it includes 0 and the negatives. So the way we can write that one is this. -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. So you can see that this set just goes both directions instead of the natural numbers which just goes one direction. Rational numbers, this is a little bit more difficult to show in set notation or even on a number line. So we're just going to say what that is. This is any number that can be expressed as a fraction. So let's talk about what that means, what it means to be expressed as a fraction. 10. Is that a rational number? Yeah, because 10 is 10 over 1. How about 7.5? Is that a rational number? Sure, because that's 75 100ths. So you could write that as a fraction. How about the square root of 2? Now if you put that in your calculator, you're going to get a number that has a decimal that goes on forever. And if you've learned about this type of number, which is called irrational, you know that it never repeats. It goes on forever and it never repeats. So that would not be a rational number, okay? Now, the real numbers are any number that can be put on a number line. Okay, so let's talk about what that means, any number that can be on a number line. So how about 7? Of course. How about 7.5? Sure, we can put that on a number line all day long. How about a number like pi? Now, pi is not rational. That decimal goes on and on and on forever. But we do know that it is on the number line somewhere. It might be hard to show exactly where it is, but we can do it. It is on the number line. So pi is considered a real number. In fact, all the numbers that we've been dealing with in this class fall into this category. This is the most inclusive category of these 4 number sets. Okay, let's take a look at some of the key concepts that we developed along the way here. Universal set, subsets, and complements. Okay, so these ideas all work together. We'll take a look at them and then we'll do some examples as well. So I want to start with the universal set. Any problem that has a universal set is basically saying this problem concerns elements of this set only. Okay? So in this case, with this one, we're defining the universal set as a set of all x such that x is between -2 and 10, and it's not inclusive of -2 and 10. Okay? So that's the full set under consideration for this example. Now we have a couple sets here. I have set A, which is all x such that x is less than or equal to 8, and x is an element of the positive integers. So counting forward, going as far as we need to, goes on forever, positive integers. However, x is less than or equal to 8, so that's going to limit what's in set A. Set B is just defined by showing you some elements, -1, 6, 7, 11, and 20, and then set C is 3, 4, and 5. Okay? So let's take a look at the subset idea. To explain, a subset is just a smaller piece of a larger set. And you can see here that C is a subset of our universal set. Every element in C is also in U. So we can write that like this. C is a subset of U. This little symbol stands for subset of, and this tells us that every element in C is also in U. And you can see that 3, 4, and 5 are definitely between -2 and 10. Okay, let's review a simple Venn diagram. They always have an outer rectangle. That represents the universal set, or all the elements under consideration for the problem. And then inside you get one or more circles that represent individual sets that are also part of that problem. So here's my basic Venn diagram. What we're going to do is we're going to populate it with the numbers as indicated by what our universal set is for this problem and what set A is for this problem. Now the easiest way to populate a Venn is to start in the center and work your way out. So let's do set A. The set of all x such that x is less than or equal to 3 and x is an element of the natural numbers. So that would be 1, 2, and 3. That's it. That's what set A is. 1, 2, and 3. Now let's look at what's left. In other words, what's in this universal set that's not in set A. So the universal set is all x such that x is between 1 and 7 inclusive. So 1, 2, 3 count, but they're already shown in set A. So we don't put them outside in the universal set. But 4, 5, 6, and 7 are also in the universal set, and they're not in set A. So we could put 4, 5, 6, and 7 inside the rectangle. Okay? So a few words about what this shows us. The universal set is everything in here, both the numbers outside and the numbers inside the circle. So that's all the numbers that are under consideration for this problem. Set A is a subset of the universal set, and it contains 1, 2, and 3, as specified by that. So we've got our 1, 2, 3 in there. Okay, let's do a more complex Venn diagram. This one deals with intersections, and you notice I have 2 circles in my rectangle, and there's this area here where the circles overlap, and that is the intersection of 2 sets of A and B. So let's take a look at our universal set. All x such that x is less than or equal to 15, and x is an element of the positive integers. Set A, 4, 7, 8, and 10. Set B, 6, 8, 10, and 14. Okay, now populating these Venns is similar to the last one. It's best to start inside and work your way out. So what is the intersection? what elements are in both A and B? That's what intersection means. And I have an 8 and a 10 in A, and I have an 8 and a 10 in B. So I can put my 8 and my 10 right there. Now this portion, it contains all the elements in A that are not in B. So this would be 4 and 7. And this part here contains all the elements in B that are not in A. So that would be 6 and 14. Now here's the last step that people forget. You need to put the elements outside that are in our universal set that aren't in A or B. So what do we got? The universal set is all positive integers less than or equal to 15. 0 is not positive, so let's start. 1 isn't there. 2, 3, I got a 4, I don't have a 5. 6 we have, 7, 8, we don't have 9. 10 we have, no 11, no 12, we can put that over here, no 13 up there, and then 15. It's included, so we can put the 15 over there. Okay? So all I just did is I looked at the universal set and figured out which numbers aren't in here or here and put them around the outside. And that's our completed Venn diagram for this situation. Action. Okay, let's look at some of the problems where we shaded different regions based on the notation. Before we start, I just want to review a couple things. The union of A and the complement of A, we talked about that. What is that going to end up being? It's always the universal set. Because A is some set within the universal set. The complement of A is just everything that's not in A. So together, these two things are going to add up to the universal set. Okay? Now think about this one. What's the intersection between A and the complement of A? If you got the null set, you're right. Because by definition, these two sets contain no common elements. A, the complement of A is everything else in U that's not in A. So the intersection of these two is always going to be the empty set or the null set. Okay, so I've got 3 Venn diagrams for you to shade. If you're feeling bold, pause the video right now and see if you can get the shading right on all 3 of these. Here's your notation for what to shade. Okay, let's take a look at this first one. Something that's in A or B, but not in both. So what would I shade for A or B, but not both? That would be this area here, plus this area here. Okay, so that's the both, and outside is not in A or B. Okay, now these are going to get a little more tricky with notation. This is the intersection of A and the complement of B. So intersection means shared elements. So what elements are shared with A and the complement of B? Now this one is tricky. A, it means it has to be something that's in the A circle, and the complement of B is everything that's here, because this part of A is also in B. So this one we get shaded like this. Okay? So that's the intersection of A and the complement of B. Now this last one is kind of fun. The intersection of the complement of A and the complement of B. So what elements are both not in A and not in B? And that would be the outside of both circles. So all the elements that I've shaded there are at the same time both not in A and not in B. One of the last lessons that we did in this chapter involved numbers in regions. Not like the numbers themselves, but the amount of things or numbers of things in each region. And this was the building block upon which we did the problem solving, which was our last lesson. Okay, so a little bit about notation. When you see numbers in parentheses in a set diagram, in a Venn diagram like that, what it means is that there are 6 things here, 7 things there, 15 things there, 4 there. And let me do my labels. These are sets A and B, okay? Now, Once you have that, we can start to answer some questions. I put all my questions in notation because that's a little bit harder to suss out. Okay, so if you want to pause the video right now and see if you can get all those, do that. All right, let's check how you did. The number of elements in A is the A circle, so it's 6 plus 7, so that's 13. The number of elements of B in B are this area with these two, so that's going to be 22. The number of elements in the universal set is everything, all 4 of these numbers. Remember, that means that there are 4 things in this universal set that are not inside A and B. So we just need to add these all up. That's 13 plus 15 is 28 plus 4 is 32. So this would be 32. And then when that's known, what I like to do is write this on my diagram. That tells us that we know how many elements are in the universal set. Now it's going to get a little more complex. Now we want the number of elements in the intersection of A and B. So the intersection is where the elements there are in both sets, and it's the intersection of these two circles, so that's 7. Now the union of A and B means everything in both sets. So that's 6 plus 7 is 13, plus 15 is 28. Now it starts getting a little confusing when we use complements, so let's take a look at those. These last two. This is the number of elements in the complement of A and as it intersects B. Okay? So remember, intersection is the more limited case. It has to be elements that are in both these things. So what elements are in B and also in the complement of A? So we know from the last board, that's this region here, this part, that's in B and it's in the complement of A, meaning that it's not in A. So this number here is how many elements are in B but not in A. So that's this guy, 15 there. Okay, let's do this last one. It's a little bit more complicated, so let's take a minute to look at the notation. That's the union, so that's more inclusive. That's everything that's in the complement of A and in the complement of B. Okay, so this is the union of the complements of both these sets. Okay, so check it out. There's an easy way to do this. This region here is the intersection. There are 7 in the intersection between A and B. These are the only things that are not in the complement of one or the complement of the other. So we subtract that. Crap, do it again. So okay. Let's take a look at this last one. It's a little bit confusing. This is the number of elements in the union of the complements of both A and B. So let's think about that. The complements of A and B are just the things that are not in either of those sets. However, we have a union. So that means we're going to add stuff together. It's more inclusive. So the complement of A is everything not in here, and the complement of B is everything not in here. But since it's a union, we can include a lot of other stuff. In fact, the only thing that doesn't belong in this group is the intersection. These things are both in A and both in B, so they can't be excluded. So we're going to have 32 minus 7, and this is going to be 25. One last topic, problem solving. You worked through a bunch of different problems with problem solving where you had to create a Venn diagram just based on information. So I want to do one of those. I'm not going to answer questions about this Venn, I'm just going to show you how to make it. Okay? So, here's our situation. 80 students, 62 like math, 49 like history, and 12 like neither. So what we have to do is get the correct numbers into the Venn diagram. So your entry is always look at all these numbers and figure out which ones you can throw on the Venn without doing any calculations. So first off, 80 students total. That's our universal set. So we put this here, U is just 80. Now I can't put these two numbers on yet because the 62 that like math, some of them are here and some of them are there. And I don't yet know which ones are where. Same thing with history. This 49 people that like history, some are here and some are there. And we don't know what that is. You notice also, they didn't tell us what the intersection was. If they told us who liked both, then it would be pretty easy to figure out the math and the history that go there. But we don't have that. So you have to use this sort of algebra trick. What we do is we label these three regions, A, B, and C. And then we do a little bit of algebra. Oh, I missed something. See if you can figure out what I didn't put on there that I need to. 12, like neither. That goes here. Okay? All right, so I needed that because now I can write A plus B plus C. That is all the numbers that go in these three regions. That's going to be 80 minus the 12 that aren't in those regions. So A plus B plus C equals 68. Now, we're almost there. We know that math, we have 62 people in both these areas. So we're going to get A plus B equals 62. Okay? So far, so good. Now that leaves C. If A plus B plus C is 68, and A and B are 62, then that's going to leave 6 left over for C. And that we can throw on our Venn diagram right there. Okay? Now we can work our way across. Since I know history is 49. If 6 of them are here, that means 43 have to be right there. Okay? So that gives us our history total, 49. 6 like history only, and 43 like both history and math. Now let's move on and figure out what goes in A. If 62 like math, and 43 of them are here, then that's 19 left for math, but not history. Now when you get to this stage, if you want to be sure, what you do is you just count up all of these numbers, everything that's in the rectangle, and that should equal your universal set. And if you do that with this problem, you're going to see that indeed it's right. Now that you've watched the video, take a moment to jot down any additional notes, some questions, or a quick summary of the lesson. You can also re-watch the portions of the video that were a little bit challenging for you. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.